Hello everyone, and welcome to my presentation on the topic of stacks. Today I'll be explaining the concept of stacks, their properties, operations, and applications in data structure. Welcome to this presentation on stacks. A stack is an abstract data type that acts as a collection of elements, with two main operations: push, to add an item to the stack, and pop, to remove the top item. Stacks operate on the last in, first out, LIFO principle, meaning the last item added is the first one to be removed. To understand this better, imagine stacking plates in a pile. The last plate you add to the top is the first one you take off. This simple yet powerful concept forms the basis of stacks. Now let's explore some real-life examples of stacks to understand their applications better. First, consider a stack of plates in a cafeteria. You add plates to the top of the stack, and the plate on top is the first to be removed. This perfectly demonstrates the last in, first out, LIFO principle. Next, think about the undo functionality in text editors like Microsoft Word. When you perform actions, they are stored in a stack. The last action you performed is the first one you can undo. Another example is browser history. When you visit websites, they are stored in a stack. If you press the back button, the last site you visited is the first one to reappear. Finally, using diagrams or visualizations can make these concepts even clearer and easier to understand. Now let's discuss the basic operations of a stack. These are the key actions that make a stack functional. Push. This operation adds an element to the top of the stack. Think of it as placing an item on top of a pile. Pop. This removes the top element from the stack. You can imagine taking the topmost item off a pile. Peek. This operation allows you to view the top element of the stack without removing it, helping you check what's at the top. Sempty. This checks if the stack is empty, which is helpful to avoid errors while trying to remove items from an empty stack. IsFull. This checks if the stack has reached its capacity, ensuring no more items can be added. For example, imagine managing a pile of books. You can add a new book on top using push, remove the top book using pop, and check the title of the top book without removing it using peek. These operations make the stack structure efficient and easy to use. Welcome to this presentation on stack implementation. In this session, we will explore two primary methods of implementing a stack, using arrays and using linked lists. An array-based implementation of a stack provides a fixed size, which makes it simple to use but limits the stack's capacity. On the other hand, a linked list implementation is dynamically sized, allowing for more efficient memory usage. Each element in this structure is a node in a linked list, connected to the next node. We'll also review code examples for both methods in languages like Python, C++, or Java, and discuss the standard implementations available in various programming languages, such as Python's list and Java's stack class. Let's dive in and explore the details of these stack implementations. Now let's go over the key operations in a stack. The push and pop operations. First, the push operation adds an element to the top of the stack. If we're working with a fixed size stack, like an array, there's a limit to how many elements can be added. When this limit is reached, attempting another push will cause a stack overflow, meaning there's no more space to add new items. Next, the pop operation removes the top element from the stack. However, if we try to pop from an empty stack, we encounter a stack underflow, an error indicating that there's nothing left to remove. We also have overflow and underflow conditions. Overflow occurs when we try to add to a full stack, while underflow occurs when we attempt to remove from an empty stack. Both situations highlight the limitations of the stack data structure, especially when using a fixed size. Finally, to illustrate, we'll look at diagrams showing each operation with arrows. These diagrams help us visualize items being added to or removed from the top of the stack. Now let's explore some practical applications of stacks in computer science. First, we have the function call stack. Stacks play a crucial role in managing function calls, especially in recursive functions. Each function call is placed on top of the stack, ensuring that the most recent call is completed first. This last in, first out structure helps manage the sequence of function execution. Next is browser history. When you navigate through web pages, the last page you visited is stored at the top of the stack. This allows you to easily go back to previous pages, accessing the most recent one first. Another application is the undo mechanism in software. Many programs, like text editors, use a stack to keep track of recent actions. This allows users to undo the most recent action first, enhancing user control and flexibility. Lastly, we have balanced parentheses checking and expression evaluation. Algorithms that check for balanced parentheses or evaluate mathematical expressions use stacks to ensure that each opening symbol is matched with a corresponding closing symbol in the correct order. These are just a few examples of how stacks are essential in software and system design. Welcome to the slide on advantages and limitations. Let's start with the advantages. Firstly, this data structure is simple to implement, making it a practical choice for many applications. It provides direct access to the most recently added element, which is ideal for situations where only the latest input is needed. Additionally, it operates efficiently for last in first out, or LIFO operations, which is a common requirement in various computing tasks. However, there are some limitations. If implemented using an array, the size is fixed, which can be restrictive if you need a more flexible solution. Access is also limited to only the top element, meaning you can't retrieve other elements directly without removing those above it. This can make certain operations inefficient. In the following slides, we'll go through each advantage and limitation with brief examples to further illustrate these points. Thank you for your attention throughout this presentation. I hope this overview has provided you with a clear understanding of stacks, their advantages, limitations, and practical applications. If you have any questions or would like further clarification on any of the topics, please feel free to ask. Thank you once again.